Hello everyone, my name is Khalid. Welcome to this tutorial on psychrometric chart and air conditioning, part of the Applied Thermodynamics course for third year students in Universiti Sains Malaysia. Hopefully you find this tutorial useful, so enjoy. First question, we have a table with 6 processes. We are given the before and after points at the beginning and at the end of the process. For each point we have 2 data values, so we can find out from the psychrometric chart the other values. Then we have to calculate delta omega, delta H, and name the process. So for the first process, we have first point is dry bulb 30 degrees Celsius and relative humidity 95%. So this is the 30 degrees Celsius dry bulb line crossing with the 95% relative humidity. So we can find out how much enthalpy here. Also the wet bulb, we have this is 30 and this line is 29. So it is around 29.4 degrees Celsius. Finally, we go to the right horizontally to find out how much omega in gram per kilogram dry air. So we write down the data. Second point will be dry bulb 30, which is similar to the first one, which indicates that the line is vertical line. Relative humidity is 40%. So we cross the 30 degrees Celsius with the 40% relative humidity. So we extract the data directly. So this is omega. And the dot line will lead us to the wet bulb and enthalpy. So delta omega will be 10.5 minus 26 will give us minus 15.5. Delta H is 58 minus 97 will give us minus 39. You can see here the process is vertical going from up to down. So this is pure dehumidification. Point 2, we have 31 degrees Celsius dry bulb and relative humidity 80%. So this is 31 line crossing with the 80% relative humidity. So we extract the data directly. This is the enthalpy and this point is the wet bulb. And we go here to the right to take the omega value. Second point is 41 degrees Celsius dry bulb and omega is 19. So this is the 41 line crossing with omega 19. We can see that both points are on the same enthalpy line and same wet bulb line, and the point is going down. So this is called adiabatic dehumidification. So delta omega is 19 minus 23 will give us minus 4. Delta H is 90 minus 90 will give us 0. Since this is a adiabatic process, we don't have any. Since this is adiabatic dehumidification, the enthalpy change will be 0. So process number 3, we have similar point 41 and 19 from the previous process. So we copy the data directly. Second point is 27 degrees Celsius dry bulb and enthalpy 76. So this is the 27 line. And here is 76 enthalpy line. So we extract the data directly. So we take the omega value. We can see here that both points has same omega value, meaning that they are on the same horizontal line. So there is no addition or removal of water. The absolute humidity is constant. So this process is going from the right to the left in horizontal line, which is known as sensible cooling. In this case, delta omega is 19 minus 19, which is 0. Then enthalpy is 76 minus 90, which is minus 14. And the process is sensible cooling. Next point, we have 27 and 76, which is the same point. So we just copy the data. The other point is wet bulb 15 and relative humidity is 100, meaning that we are on the saturation line. So this is 15 on the saturation line. In this case, wet bulb will equal dry bulb. Both will be 15. So we take omega value and H value. So delta omega is 10.6 minus 19, which will give us minus 8.4. Delta H is 42 minus 76 will give us minus 34. So we draw the process line. We can see that the humidity is dropping. So this is dehumidification. Also, it goes from right to left. So this is cooling. So the process is cooling and dehumidification. Next process, we have same point 15 and 100. So we just copy the data. The other point is relative humidity 50% and H is 33. So this is H33. We cross the line with the 50% relative humidity. So dry bulb will be here 17 and we take omega value. So we can see here the process is dropping down but on this specific line. So this is the specific volume line. So this process is constant volume process, which is known as isometric, and since it is going down, so it is isometric dehumidification. So delta omega is 6 minus 10.6 will give us minus 4.6. Delta H is 33 minus 42 will give us minus 9. Last process, we have 17 dry bulb and 50% relative humidity, which is the second point. We can see here 17 dry bulb and 50% relative humidity. So we just copy the data. So second point is dry bulb 28 degrees Celsius and omega is 6. We can see here omega is constant, meaning that delta omega is 0. This indicates that the process is horizontal with no addition or removal of water. So this is 28 degrees Celsius crossing with the omega equals 6. So we can see here the process is horizontal and going from left to right. So it is sensible heating. So delta H in this case is 44 minus 33, which will be a positive value, 11 kilojoule per kilogram. Question number 2, we are giving the ambient temperature and the room inlet temperature. We have to compare between two different systems in terms of the consumption of the power. So first system is the hydronic all water system with desiccant dehumidifier, while the second one is the conventional compression refrigeration all air system with Freon as the refrigerant. So first system, we have here the room inlet temperature is given and the ambient temperature is given. So we have to place first the desiccant dehumidifier. So the desiccant dehumidifier will reduce the humidity, but it will increase the temperature. Then we put after that the cooling coil, which is cooled by chilled water. For the second system, we have the conventional compression refrigeration. We have first the cooling coil, which is the Freon cooling coil. Then we have to add another heater to achieve the target room inlet temperature. So we can draw both processes on the psychrometric charts. So ambient is at 34 degrees Celsius, which is this line, crossing with 55% relative humidity. So we can take directly omega value and H value. Second point is the room inlet temperature at 28 degrees Celsius and 50% relative humidity. So for the hydronic system with desiccant, we have the desiccant first, following the adiabatic dehumidification line, which is parallel to this dot line. Then we have the chiller or the cooling coil, which is a horizontal line. So we can extract the enthalpy data. For the second system, we have conventional cooling with compression refrigeration. So the coil dew point is 15 degrees Celsius. So we just connect between the ambient and the dew point. And since the coil efficiency is not 100%, so the outlet will be higher than the dew point. So we assume that the coil outlet is the heater inlet. So the heater will follow the same horizontal line to the room inlet. So the heater line will cross the coil line at the coil outlet and the heater inlet point. So we take the data from this point, the enthalpy. So omega for ambient is 18.5 gram water per kilogram air, and omega for room inlet is 12 gram water per kilogram air. In this case, the drop in omega, delta omega, will be 6.5 gram of water per kilogram of air. So we have to change it into kilogram per kilogram for the calculations. And since the mass flow rate of air is 1 kilogram per second, so mass flow rate of water will be mass flow rate of air multiplied by delta omega. For the desiccant regenerator, we are given the latent heat HFG equals 2256.5 kilojoule per kilogram. So we can calculate how much thermal power needed for the regeneration of the desiccant dehumidifier, which is the mass flow rate of water multiplied by HFG, which will give us 14.67 kilowatt. Note that this heating power can be taken from renewable resources such as biomass or solar heating panel. As for the chiller, we can see the power required is between this point and this point. So Q for the chiller equals M air multiplied by delta H, which will give us 23 kilowatt. So the total power for the hydronic system number 1, will be 14.6 plus 23, which will give us 37.67 kilowatt. Now we calculate for the second system, which is the conventional compression refrigeration. So the power for the cooling coil is mass flow rate of air multiplied by delta H. So from the psychrometric chart, we can see this power is here between the ambient and the coil outlet point. Which will give us 33 kilowatt. The additional power required for the heater, we can see the power from the psychrometric chart. This is the heater. Enthalpy will be between 59 and 49, which will give us 10 kilowatt. So the total power for the conventional compression refrigeration system is 33 plus 10 will give us 43 kilowatt, which is considerably higher than the hydronic system, which is 33 kilowatt, including the heat required for the desiccant regeneration process. So we can conclude that the hydronic system is more power efficient compared to the conventional compression refrigeration. So question number 3, we have a Y-shaped mixer to mix two streams of air. We have to determine the properties of the air at the outlet of the mixer. So we use the psychrometric chart to do the mixing. So point number 1, we have dry bulb is 32 degrees Celsius and relative humidity is 40%. So this is the dry bulb 32 degree crossing with 40% relative humidity. So we can extract the data directly for omega and H. So point 2 is at dry bulb of 12 degrees Celsius and 90% relative humidity. So this is the dry bulb line crossing with 90%. So we draw the mixing line between the 2 points. So the mixer outlet should be a point on this line. So from psychrometric chart, we found H value and omega for point 1. Also, we need the specific volume. So this is the line for specific volume. Here we have the flow rate is giving in volume flow rate. So we have to convert it into mass flow rate. So we have the specific volume of the flow, which is the reverse of the density. So mass flow rate of air will be the volume flow rate divided by the specific volume. which will give us flow rate of 22.7 kilogram per minute. Similarly, we calculate the mass flow rate for stream number 2, which will give us 30.5 kilogram per minute. So we can do either mass percent for stream 1 or mass percent for stream 2. So this is 0.1 and this is 0.2. Let's say 0.3 is somewhere here. So if we want to take mass percent for 0.1, the rule of thumb, we take 0.1, so we take the opposite distance here is between 2 and 3. So mass percent for 0.1 will be 3 minus 2 divided by the total distance, which is 1 minus 2. So we can take this one from omega axis, or we can take it from temperature axis, or we can take it from the enthalpy axis. So in this case, mass 1%, which is mass 1 divided by total mass, mass 1 plus mass 2 will be H3 minus H2 divided by H1 minus H2, or omega 3 minus omega 2 divided by omega 1 minus omega 2, or T3 minus T2 divided by T1 minus T2. So in this case, for mass 1 fraction will be 22.7 divided by the total mass is 53.2, which will give us around 42.6 or 0.4269. So in this case, this number will equal the H, the omega and the T. So from each one we calculate one value. So from first one we calculate H3, from second one we calculate omega 3, and from third one we calculate T3. So H3 will equal 45 kilojoule per kilogram. Omega 3 will be 9.6 gram. T3 will be 20.6%. Alternatively, we can find just one of them, then take the rest of the data from the psychrometric chart. So we can see here the dry bulb temperature is 20.6 degrees Celsius. So this is the point. So we can take H value and omega value directly from the psychrometric chart. But of course, it will be less accurate. Question number 4, we have a cooling tower. We have to determine how much the mass flow rate of air and the mass of makeup water. This is schematic of the cooling tower, and this is the required steam table to calculate the enthalpy for water. So we can draw simple balance here. Air is coming from the side and going upwards. Water is coming from the other side, then through the spray, then going down to the water tank where we have the makeup water to replace the evaporated water. We put the number in here. Is number 1, number 2, number 3 and number 4. So here we have mass air entering at point 1, mass air exiting at point 2. Then mass of water that we intend to cool down entering, then mass of water exiting M4. For the air mass balance, the dry air entering equals the dry air exiting. So M air dry 1 entering equals M air dry 2 exiting, which is in general M air. But the air entering is not dry, it has humidity, and it will be uploaded with further humidity once it exits. For the mass balance of water, we have mass of water entering equals mass of water exiting plus mass of the evaporated water, which is also known as the makeup water, since the evaporated water is exactly the same as the replacement makeup water. So in this case, the makeup water can be calculated as mass of water entering minus mass of water exiting. We studied already how to calculate mass of water from the psychrometric chart. So mass of water is mass of air multiplied by delta omega, which is omega 2 minus omega 1, since the air will be uploaded with the evaporated water. For the energy balance, we assume that the work equals 0 and the heat transfer equals 0. So from first law of thermodynamics for open cycle, we will have the enthalpy balance equals 0, meaning that enthalpy inlet equals enthalpy outlet. So the inlet is mass of air 1 multiplied by H1 plus mass of water 3 multiplied by H3 entering the cooling tower. Then the exit is mass of air 2 H2 plus mass of water exiting 4 H4. So we can rearrange the equation using mass flow rate of water. So mass flow rate of air in this case will equal. So let's see what are the knowns and the unknowns. Water is entering at 40 degrees Celsius, so we can take enthalpy of water at 40 degrees Celsius directly. It is HF for the liquid water. Then water is exiting at 30 degrees Celsius, so from steam table also we take at 30 degrees Celsius, we take HF, which is the enthalpy of water exiting. So this one will be H4 while this one will be H3. So we already know H4 and H3. We still have to know how much H1 for air and H2 for air. We use psychrometric chart for that. So air condition at the inlet, we have 22 dry bulb and 16 wet bulb. So this is 22 dry bulb line and this is 16 wet bulb. So we cross between the two lines. So this is point 1. We can take all necessary data. We take omega and H. The exit condition for air is 32 with relative humidity of 95%. So this is the line 32. We go to cross with the relative humidity line. So we collect the data for omega and H. So from the psychrometric chart, H1 equals 44.7 kilojoule per kilogram dry air. Omega 1 is 8.8 gram water per kilogram air. Note that for the calculation we have to change it later on to kilogram per kilogram. We cannot use gram per kilogram. H2 will be 106.6 kilojoule per kilogram dry air and omega 2 will be 29 gram. We already took the values for H3 and H4 from the steam table. So now we can key in directly to the MA equation and calculate how much mass flow rate of air. Mass flow rate of water, which is M3, is given is 40 kilogram per second. So in this case, mass flow rate of air will be 28.17 kilogram per second. So now we can calculate directly the makeup water that is required to keep the water level in the tank constant. Makeup water will be MA multiplied by delta omega, which is omega 2 minus omega 1. So we convert omega in this case to kilogram per kilogram. So the makeup water is 0.568 kilogram per second. So last question, question number 5, we have a simple air conditioning system based on conventional compression refrigeration all air system. The ambient temperature is given and the comfort temperature or the room temperature is given. Also the sensible heat factor for the load. Basically the sensible heat and latent heat loads are given. The mixture condition at the mixing box also is given. Also we can see here in the drawing we have here the dew point for the coil also is given. First is the ambient is 33 degrees Celsius and 70% relative humidity. So we can find all the information from the psychrometric chart. So this is the 33 dry bulb. We cross that with the 70% relative humidity line. Second point is the room outlet temperature or the room temperature, which is 25 degrees Celsius and relative humidity 50%. So this is the 25 degrees Celsius dry bulb line, and this is the 50% relative humidity. So connecting the ambient with the room outlet will give us the mixing box. So we can take other data such as the enthalpy and omega. So in this case, the ambient is point number 2 and the room temperature or the room outlet temperature is point number 1. So we can draw the mixer here. So this is point 2 and this is point 1. This is just like the Y-shaped mixer we just took before. So the outlet from the mixer will be point 3. So the recirculation is 80% or fresh air is 20%, means point 3 will be much closer to point 1. So this will be 20% and this will be 80%. So we can use either the fresh air percent or the circulation percent for the calculation. So fresh air percent is 20%, which is 0.2. So ambient in this case represents the fresh air. So again, like in the Y mixer, we take the far side, which is 0.31. This will be T3 minus T1 divided by total T2 minus T1. Similarly, we can take recirculation percent, which is 80% or 0.8. Recirculation will be represented in this case by the room temperature. So in this case, we will take the far side, which is 2 minus 3. So in this case, it will be T2 minus T3 divided by T2 minus T1. We can use either one to calculate T3. So in this case, T3 will be 26.6 degrees Celsius. So we take this value here, 26.6. This will be 0.3. The dew point for the coil is given, it is 10 degrees Celsius. So we can connect directly the coil inlet with the dew point. So this is the coil line, but we still don't know where is the outlet of the coil. A hint was given to us, the efficiency of coil was given. So we can see here the coil is in the blue line. The outlet of the coil will be somewhere here. It will be 0.4. So the efficiency of the coil is the large portion, 3/4 divided by the total portion, 3 minus dew point. Coil efficiency percent is 85%, which equal T3 minus T4 divided by T3 minus T dew point. So in this case, the only unknown is T4. We can calculate it directly. So T4 will be around 12.5 degrees Celsius. After that, the heater can be drawn as a horizontal line since it is sensible heating. So from 0.4 to 0.5, it will be a horizontal line. But we still don't know what is the room inlet temperature, which is 0.5. So let's draw 0.4 on the psychrometric chart. This is 12.5 dry bulb. So this is 0.4. Then we can draw a straight horizontal line. So the room inlet should be somewhere on this line. So how to find the room inlet condition? We have here the sensible and latent loads of the room, 9 kilowatts sensible and 6 kilowatt latent. So we can calculate directly the sensible heat factor of the room is the sensible heat divided by total heat. So sensible heat is 9 kilowatt and total heat is 15 kilowatt. So sensible heat factor in this case will be 0.6. So we have two ways for the calculation. Either we use the angle directly from here and we take this one parallel and we draw from the room outlet temperature this line. So let's simplify the chart here. So one way is to draw the 0.6 sensible heat factor line parallel to this line. Then crossing this line with the heater line will give us the room inlet temperature, which is 0.5. In this case, you need to use the geometry on the psychrometric chart. Another way, we can draw here a right angle triangle. So the latent heat is 6 kilowatts. So we can just draw a line with the length of 6 centimeter. And the sensible heat is 9 kilowatts, so we just draw a line with 9 centimeter. Then complete the right angle triangle, so we can have our 0.6 slope. So the cross will be 0.5. So we draw the line here, and this is 0.5. We take all the data from psychrometric chart, so we need to take h values for each point. So in this case, we have the cooling coil load is between H3 and H4. The room load is between H1 and H5. And the heater load is between 0.5 and 0.4. So Q coil will be mass flow rate of air, H3 minus H4. Q room is mass flow rate of air, H1 minus H5. Q heater is mass flow rate of air, H5 minus H4. However, we don't know how much the mass flow rate of air. It was not given, but we know how much the heat of room, the load of the room, which is 15 kilowatt. So from here we can directly calculate back how much the mass flow rate of air. So mass flow rate of air will be 15 kilowatt divided by H1 minus H5, which will give us 1.36 kilogram per second. Now we can calculate the load of the coil. Note that we have to divide by 3.51 to convert from kilowatt into ton refrigeration. So in this case, the load will be 9.6 ton refrigeration, since 1 ton refrigeration equals 3.51 kilowatt. Lastly, we calculate Q for the heater, which will give us 7.9 kilowatt. So this will conclude this tutorial. Hopefully you find it useful. Thank you for watching.